This is section 6.3, part 1, and we're going to be talking about vectors in the plane. And the first thing we're going to talk about is just some basic key terms and notation. So far, we have a lot of things like in geometry and physics that can be represented by a single real number, like area, time, temperature. But there are other things, other quantities, um, such as force and velocity, that you have to involve magnitude and direction. Okay, and that can't be um, found by just a single real number. All right, so what we're going to do to represent those numbers that involve magnitude and direction are directed line segments. Okay, so let me get my point ready. Okay, a directed line segment, an example, so a directed line segment, and I would write this down in your notes, has an initial point, and we're going to call that point P, and a terminal point, and we're going to call that Q. Okay, now a directed line segment has magnitude and direction. All right, and whenever I label this point P, here's my terminal point Q, and instead of in geometry when I used this for array, a directed line segment or vectors are going to be just a one-sided arrow. Okay, so when we're talking about the length, okay, of this directed line segment, that's another word for magnitude. Okay, so magnitude and length, those equal the same thing. All right, and we have a new notation for that, and it looks like this. It's going to be these double vertical lines, PQ. So anytime you see this, this is the symbol for the magnitude or the length of that directed line segment, PQ. All right. We're going to review a couple of formulas that we're going to need here in just a minute in order to find the length of that line segment. So since these line segments, okay, I can have all these different line segments, and as long as and those should be having the same slope, as long as they have the same direction and the same magnitude or length, all right, those are equivalent. Okay, and all of these same directed line segments, okay, those are all vectors in the plane. Okay, so if they all have the same length and same direction, all these line segments, then those are vectors, and we usually notate vectors with a lowercase, bold D, sometimes a W, and a U. All right. Let's review a couple of formulas we're going to need, okay? We already know that to find the length or the magnitude of a directed line segment, so magnitude is the same thing as length, and so we need to review the distance formula when I have to find the distance of a line. Okay, so the distance formula is the square root of my difference of my y's squared plus the difference of my x's squared. Okay, so that's how we're going to find the magnitude of each of these. To find that if it has the same direction, well, the same direction means that it would have the same slope. So remember how to find the slope. It's the difference of our y's over the difference of our x's. So we're going to be using those, all right? So for vectors to be equivalent, they must have the same direction and the same magnitude, or the same length and the same slope. So let's do number 1 together. Let U be represented by the directed line segment from the point P00 to point Q32. And let V be represented by the directed line segment from R equals 1, 2 to S equals 4, 4. Show that U equals V. So in order to show that two line segments or two vectors are equal, they have to have the same length or the same magnitude, and they have to have the same slope. Okay, so first of all, if I were to just sketch these, 0, 0, and 3, 2. So my initial point is 0, 0. My terminal point is 3, 2. Okay, so there's line segment, directed line segment PQ. And let me do this in a different color. So then I have 1, 2, 4, 4. Okay, and so, maybe I need to go a little bit like that. All right, and this is RS. Okay, so I know it doesn't look like it, but I'm supposed to show that these have the same length and the same slope. All right, so let's do U first. Okay, so it says U equals, and I need to find the magnitude of the directed line segment PQ. Okay, and we're going to do that by finding the distance between these 2 points. So that's going to be the difference of my y's. So 3 minus 0 quantity squared plus, oops, that should be the difference of my y. So that should be 2. Doesn't really matter in what order I do this. So that's 2 minus 0 quantity squared plus the difference of my x's quantity squared. So that's going to be 2 squared, which is 4, plus 3 squared, which is 9. So that's the square root of 13. Okay, so now let's do V. So V, I'm going to find the magnitude of directed line segment RS. So we're going to find the distance between those 2 points. So it's going to be the difference of my y's. So 4 minus 2 quantity squared plus 4 minus 1 quantity squared. That's going to be 2 squared, which is 4. It's going to be 3 squared, which is 9. Okay, so the magnitudes are the same. That's the first step. So the magnitudes were the same. Now we have to show that they have the same direction. The same direction would be the same slope. All right, so let's find the slope of PQ. So slope is the difference of my y's, so 2 minus 0 over the difference of my x's. So that's 2/3. Now we're going to do RS. So the slope of RS, the difference of my y's over the difference of my x's. So that's going to be 2/3. Okay, so I've shown that their magnitudes are the same, and I've shown that their slope or their direction is the same. So therefore, U has to equal V. Okay, so anytime you have to show that 2 vectors are equivalent or equal, okay, that means they have to have the same magnitude, same slope. All right. So now let's talk about standard position. The directed line segment whose initial point is the origin, or point 0, 0, is often the most convenient way to write equivalent line segments, directed line segments, okay? And this is called a vector in standard position. So standard position is when the initial point is at the origin. So remember, we're going to have 2 points in order to find for a vector. It's initial point and terminal point or stopping point. And for a vector to be in standard position, its initial point has to be at 0, 0. Okay. Um, a vector whose initial point is at the origin, so a vector that is in standard position, can be represented in a what they call component form of a vector. Okay, so instead of writing it with two ordered pairs, since we know the initial point is at the origin, we're going to write that as, instead of using P's and Q's and things like that, we're going to write it as V1, V2, and instead of using parentheses, we're going to use these symbols right here. So the component form of a vector is the easiest way to write a vector. And remember, this is talking about a vector that's in standard position with the initial point at the origin. And so I'm going to show you how to find the component form of a vector. Okay, so it says the component form of the vector with initial point P, which is P1, P2. So we have a vector that's not, the initial point is not at 0, 0. So we're going to take our point P and our point Q, terminal point Q, and we're going to use this formula right here. And I should have had this over that PQ. Okay, it's going to be our Q1 minus P1, and then our Q2 minus P2, and that's going to give us our component form for that vector. Okay, and again, the magnitude is given by the distance formula, but if we know this first point was 0, 0, then we can just take the square root of our component form. Okay, I know it kind of sounds confusing, but it's actually really easy. All right, so example 2 says find the component form and magnitude of the vector v that has initial point 4, negative 7 and terminal point negative 1, 5. So they want us to write the component form of this vector because its initial point is not at 0, 0. So we want to write it in component form so that its initial point would be at 0, 0. All right, so let's use this formula right here. Okay, so I'm given my two ordered pairs. This point P, this is point P, so here's my P1, P2. This would be considered my point Q, so this would be Q1, Q2. Okay, and I'm going to plug those numbers into this formula. Q1 minus P1, that's my first number, and then Q2 minus P2, and that's going to give me my component form. So let's do that. Q1 is negative 1 minus P1, which is negative 7. And then I'm going to do Q2. Oops, that negative 7. Let me do that again. All right, so Q1, negative 1 minus 4. Q2 is 5 minus negative 7. Okay, so when I simplify that, that's negative 5. That's going to be 12. So now this is the component form when I have this is my initial point and this as my terminal point. This is the component form of that vector. Now we can use the component form to find the magnitude. Okay, remember magnitude is the same thing as length. So now I'm going to call this is now vector v. Vector v is this right here. So now I'm going to find the magnitude of vector v by using the distance formula. So remember that my initial point's at 0, 0. So my other point is 0, 0, which just means when I use the distance formula, I can use this. v squared, v1 squared, plus v2 squared, which are these numbers right here. So the square root of negative 5 quantity squared plus 12 squared, 25 plus 144. So that's going to be 169, which is 13. So the magnitude of vector v is 13, and I rewrote that. I rewrote that in component form. Here's my vector v right here. Okay. So we're only going to do the first 12 problems, and the only two types of problems you're going to have is you're going to ask to show that two vectors are equal, two directed line segments are equal to each other by finding the magnitude and the slope. And then you're going to be asked to rewrite in component form and to find the magnitude of that vector v. Okay, so we're going to find vector v, all right, the component form of that vector by using this formula. And then we're going to use those numbers in order to find the magnitude of vector v.